Hi, in this video we will introduce the class of diagonalizable matrices. These are matrices which are similar to a diagonal matrix, and the focus will be on eigenvalues of such matrices. Okay, let's start with the definition. A square matrix A is called diagonalizable. A is diagonalizable if A is similar to a diagonal matrix for a diagonal matrix D. Well, remember what is diagonal matrix? Diagonal matrix is a matrix that has all of main diagonal matrix entries equal to 0. So it will have x1, x2 here, up to xn, everything else will be 0. Yes. So if matrix is similar to a diagonal matrix, we call it diagonalizable. Well, in particular, diagonal matrices are, note, diagonal matrices are diagonalizable. So being diagonal is even stronger. It is itself is diagonal. Well, we can have non-diagonal matrices which are diagonalizable. So, but these are very special case. Well, what we can say about this matrix D? Well, see that if A is diagonalizable, well, it means that there is a diagonal matrix like D such that A is similar to, yes? But that means that A and D they have the same eigenvalues. Very nice. Any two similar matrices have the same eigenvalues. But we know that the eigenvalues of a diagonal matrix are the entries on the main diagonal. So this means what? This means that the entries on the main diagonal of D are eigenvalues of A. So exactly the eigenvalues of A will appear there. Well, let me just write this as a fact. If A is diagonalizable, then A is going to be similar to diagonal matrix lambda 1, lambda 2 up to lambda n, where lambda 1 up to lambda n are eigenvalues of A itself. So it means that, well, diagonalizable matrices, we know what kind of matrix these matrices are similar to. Just put eigenvalues of the matrix A on the main diagonal. That's what we have. Well, we can use this to do some work here. It is a very nice fact that can be used in some cases to determine if a matrix is diagonalizable or not. For example, this guy here, A, well, you see that the eigenvalues of A are, well, 1, 1, 1. In other words, it is 1 multiplicity with the multiplicity is 3. Yes. So it means that if A is diagonalizable, I don't know if it is or not, but let's just assume diagonalizable. Then A is going to be similar to 3 by 3 matrix diagonal, which has 1, 1, 1 on the main diagonal. Everything else is 0. This matrix is familiar. This is famous identity matrix. This means that if A is diagonalizable, it's going to be similar to identity matrix. But remember that the only matrix similar to identity is identity. Well, this means that if A is similar to identity, we should conclude that A is equal to identity matrix. It must be the identity matrix itself. But look at this guy. This is not identity matrix. There is non-zero entry there. So this is contradiction. And we can say that, okay, this is not diagonalizable. Okay. How about this one? Okay, so this is again a triangular matrix. So eigenvalues of A are 0 and 1. Yes. So if A, well, let me call this one A, is diagonalizable, then it must be similar to 1, 0, 0, 0, the diagonal matrix which has 1, 0 on the main diagonal. Well, it means what? It means that we can find an invertible matrix. So there exists an invertible matrix P. Well, this is 2 by 2. I can write a very general A, B, C, D, such that AD minus BC is not 0, and P inverse AP must be equal to 1, 0, 0, 0. Okay. Well, I can do all the work here. Well, because this is 2 by 2 matrix, I know how to find its inverse. It's 1 over AD minus BC. Interchange the main diagonal entries, multiply the off diagonal entries by negative sign, and then this will be 1, 1, 0, 0, and here this will be A, B, C, D. This must be equal to 1, 0, 0, 0. Well, do the product of both sides. If you do that, so let me just go to the beginning. It will give us 1 over AD minus BC, 2 by 2 matrix, AD minus AB, DB minus B squared, minus CA plus A squared, minus CB plus AB. This must be equal to 1, 0, 0, 0. So two matrices are equal. That means what? That means that this entry here, which is, well, AD minus AB over AD minus BC must be equal to 1. Well, even easier to say is AD minus AB must be not equal to 0. And the other entries, like B, DB minus B square must be 0, and minus CA plus A square must be 0, and minus CB plus AB must be equal to 0. From here, you see this is A times B minus D minus B. This not being equal to 0 means that neither A is 0 nor D minus B. Very nice. We found, oh, this cannot be 0. Yes. Here, I can factor out b, and I get d minus b times b must be equal to 0. We already saw that this guy cannot be 0. So that implies that b is 0. And from here, we can factor out a. So minus c plus a times a is equal to 0. We already know that this is not equal to 0. That will imply that minus c plus a is equal to 0, and that means that a is equal to c. Here, well, b is already 0, so you multiply to two numbers, you get 0, add them, you get. So the last one is going to be true. What we have here now, if I list all the conditions I got, a must be not equal to 0, b must be equal to 0, d minus b must be not equal to 0, but b itself is 0, so that means that d must be not equal to 0, and a must be equal to 0. It means what? It means that if you take P, any matrix which has these kind of entries, A is any non-zero entry, then 0, C is equal to A, and D is any non-zero entry. So A and D are non-zero. Well, for example, we can take P to be 1, 1, 2, 0. Such a matrix will diagonalize the matrix we have. So if you do P inverse AP, you will get 1, 0, 0, 0. And yes, that means that this guy is diagonalizable. Well, this case was a little bit strange, but we handle the case with some hard work. In general, we will learn some criteria to check if a matrix is diagonalizable or not.